Okay, let's take a look at this guy here. As you can see from the title of the document, this is second order. We're taking two derivatives. Homogeneous because it equals zero. And by the way, that's pronounced homogeneous, not homogeneous. Homogeneous doesn't have that E right there. Constant coefficients. All of the coefficients in front of my y's and his derivatives are all just constants. Okay, in these, as we've mentioned in previous videos, we're always going to assume that y is of the form e to the lambda. And they didn't tell us here in the problem. I'm going to assume my independent variable is x. Sometimes it'll be t, sometimes it'll be x, and we just know from context. Okay, so if that's true, then the first derivative will be lambda e to the lambda x, and the second derivative will be lambda squared e to the lambda x. And you can check those details on your own. Okay, then that means we're going to plug this guy right here, plug this guy right here, and the original right there. And that'll give us lambda squared e to the lambda x minus 8 lambda e to the lambda x plus 15 e to the lambda x equals 0. And we've got this constant factor here of e to the lambda x that we can factor out. Now, e to the lambda x never equals 0. So I can just divide both sides by that, and I get what's called my characteristic polynomial. To her. Which is lambda squared minus 8 lambda plus 15 equals 0. Now, I want you recall our dE. I want you to think about this. Our dE looked like this. We are going to get so good at this particular kind of dE that we are going to skip going through all this work. This is the work that's going on in the background. But pretty soon, we're just going to start jumping straight to the characteristic polynomial. And notice how it works here. The order of the derivative will match the power on lambda. And we just keep all the same coefficients. Like the 8, the 15, first derivative, first power. Zero order derivative, y to the 0 or lambda to the 0 power. That's where you got to be careful. Is this guy here, we're taking zero derivatives. This is the 0 ordereth derivative. This is lambda to the 0 power, which is just 1. First derivative, first power, second derivative, second power. Okay, now that's a quadratic that factors. So I'm just rewriting it here for completeness. Now I see a lot of students that make it all the way to DE. They make it to this class and they don't know how to factor. Like, honestly, I don't know how you made it this far if you don't know how to factor. We are going to be doing a lot of factoring. Please do not go through all the work of using quadratic formula here for something that you should just be able to factor in your sleep. But if you have to, quadratic formula gives you the same solutions, 3 and 5. Okay, so that means we have two different solutions here. We've got, say, y1 equals e to the 3x, and y2 equals e to the 5x. Now, these guys are linearly independent. Remember from our theory of solutions videos, a second order dE has a general solution that is just the linear combination of two linearly independent solutions. Anytime you get e raised to different powers, these will automatically, you don't have to check, these will be linearly independent. So I'll note here, like I'll put it in more general terms. E to the AX and E to the BX are linearly independent. That's the good one, as long as A and B are different. With a second order DE, we only need two linearly independent solutions. So then my general solution is y equals C1 times the first guy, and order doesn't matter here. I could have put these in the other order. C2 e to the second guy. That is the general solution to this second order homogeneous with constant coefficients differential equation. That's a good place to stop.